Hello, welcome back. So in the previous video, we discussed a little how we can have this general form of the equations for a dynamical multi-body dynamic system, and we introduced a few terminologies. Now let's look at a couple of analyses, very important and fundamental analysis you can do on any mechanical system, including multi-body systems. And this one that we'll be talking about is inverse dynamics. So inverse dynamics, what did I do? So inverse dynamics, it is a process of finding, let me say it first, then I write it down. It's the process of finding the forces that drive the system if you know fully how the system is already moving. So it's the process of, what do you see? You see just my head. That's not good. What can I do? The process of solving for the driver or driving forces if the motion of the entire system is fully prescribed. So if you know exactly how every particle is moving for every time during your simulations, that can give you the forces that cause the motion in a process that is called inverse dynamics. It is usually the case when we have the actual system, or at least some understanding of what the system is, and we have measured the movement of the actual system. We want to find out what was causing the motion. Or, for instance, we are designing a system. We want to run this hypothetical scenario that I am moving, my system is moving in a certain way. What would be the driving forces in that situation, which is very important for a very important step in designing engineered systems. So for each of them, maybe an example would be, so for the first case, when we have the system, a very common example in my field, human movement / robotics, is you want to understand human movement. So example one, you have your human walking around or running or do whatever activity they need to do. You have some sensors like cameras or force plates that measure the forces that the ground is acting on the body. You measure kinematics, all the movements and all the external forces acting on the system. So you measure body movements, all the joints, movements, plus what is called ground reaction forces. And the goal is often to find what are the joint torques in the body that cause the movement. So for instance, a few examples of why you are interested in finding that is in sports. You have an athlete performing an activity. You want to understand the mechanisms of injury. So you ask your participants to perform a movement. They then you measure the movement through inverse dynamics. You calculate the torques in each joint and try to relate that to the tissue properties and limits of human movement to try to understand when and how one movement might lead to injury. So that's one example. Another example, more engineering. Example 2 is when you want to design a system. For instance, you have this robot. This is your robot. It has the end effector, and it's a robot in a manufacturing plant. It has to carry some load from one point to another. So you know that you want to, for instance, move with certain velocity and finish your movement in a certain time. So your movement is fully prescribed. You know your payload. Through inverse dynamics, you can calculate what is the torque in each of the joints of the robot, which, for instance, can lead to proper sizing of the motors for the robot. So known movement plus payload. This gives you joint torques for motor sizing, for instance. Motor sizing. As you can see, we always try to find the driving forces that cause the motion, either actual motion or hypothetical motion that doesn't exist yet, but we know what it is, what we want. So that is the goal of inverse dynamics. So let's look at the simplest case. When you have a multi-body system without any constraints, and your forces, by forces I mean generalized forces, that includes force or torque. Forces, this is R at the joints, and I'll give you an example when it is not the case, and that complicates things a little. So without constraints means that your number of generalized coordinates is the same as your number of degrees of freedom. So in this case, we know the equations of motion is m q double dot plus all these extra effects, f functions of q dot possibly t equals q, the vector of your generalized forces. So you know the motion. So q is known, q of t. That means q dot of t and q double dot of t and all the other derivatives of it are known. And you know the effects of environment, for instance, gravity acting on the system, that goes into this F. So you know Q double dot, you know M, mass matrix, you know all these other effects, how they're affecting. What you can do, you can calculate Q, your forces that are associated with each of these joints or generalized coordinate that you have in your system. For instance, this includes e.g. your torques, tau, or some forces if you have a linear motion. So these are your driving forces that cause such motions. So that is the simplest case, just to let you know how we can use the equations of motion of the system to calculate the forces. But sometimes, often maybe, not often, sometimes the equations or the system you're dealing with is more complicated than that. So if there is constraints, it is unavoidable. If you have non-holonomic constraints, you cannot avoid that. Or for whatever reason you choose to have more generalized coordinates than degrees of freedom, in those cases you will have constraints. Or if driver forces are not at your joints, things become more complicated. And in the next videos, we kind of cover a little bit of how we can handle those. So for this case, you can again look at the example that we have, 4-bar mechanism. So you may have your equations written in terms of a single generalized coordinate q, and you know the motion, but the force that you are interested, the force that causes the motion, is not associated with that generalized coordinate. So it's not a torque. It is some other force acting somewhere else on the system. So in those cases, we have to do a little trick, transform things back and forth between different dimensions to be able to solve that. So the last thing I want to mention is, if I look at this equation, you can see that for most of the cases, well, in all inverse dynamic cases, this one shown is simple, even if we have more complex situations. Inverse dynamics, i.e. inverse dynamics, always involves solving algebraic equations. And this is huge as compared to forward dynamics that we'll see next. Algebraic equations are potentially much faster to solve than differential equations, for instance. And if you somehow can change your perspective or assumptions in the system, instead of running a forward dynamics, which is solving differential equations, you can solve a kind of different, similar situation when you have inverse dynamics. You can speed up your process significantly. But it is important you're always in inverse dynamics dealing with algebraic equation. So, okay, this is the topic of inverse dynamics, a very, very rudimentary introduction into inverse dynamics. We will expand on this later on as we see more. And the only thing remains for this module is forward dynamics, and that is the next video. So until then.